Hey everyone, welcome to Xpert Insights, exclusively produced by Sinex Design. Apologies for being a little late. My name is Devin Khan, and I'll be your host for this session, live on Zoom and on Facebook. So a few of you are wondering what is Xpert Insights and who Sinex Design is. For those of you just tuning in, we're a pioneering company in the field of integrated circuit design services and microelectronics with a legacy that spans 15 years, and we're just getting started. We've witnessed and embraced the evolution of technology, consistently adapting to deliver cutting-edge solutions. Think of Xpert Insights as a live webinar series that dives deep into the world of technology. This series is designed to provide professionals, enthusiasts, and I'm sure most of you here who are students or laymen, with valuable insights from the industry, with experts covering a wide range of topics in tech. During each session, we'll feature thought leaders or innovators sharing their knowledge on emerging trends, cutting-edge developments, and practical applications in tech areas such as IC design or data engineering, artificial intelligence, and a lot more. You'll also be able to ask a lot of questions towards the end of the session. So whether you're looking to sharpen your skills, stay updated on industry advancements, or even gain insider knowledge, Xpert Insights is your go-to source for all things tech. Now, I do have a few reminders that I'd like to share with everyone. Firstly, please keep your microphones muted and your cameras off during the session. We'll have a Q&A session towards the end, so that's when you can ask your questions, and you can send them on Zoom. Secondly, we'll be releasing an attendance form in the middle of the session, so please do not forget to click the link in the comments below for your attendance. It's not there yet, but it will be. Filling out this form is required for your certification, so do not fill it. If you don't fill the form later on, we cannot release your certificate. So please be mindful of that. And don't worry, we'll update you as the session goes on, so in case you forget. Today we're hopping on the I3C bus, learning about I3C interface versus interface protocols. I'm sure many of you non-engineer laymen, like myself, are wondering what an I3C interface is. They're a next-generation communication protocol developed by the MIPI Alliance. I could be saying that wrong, but we'll roll with that right now. During this session, we'll delve deep and help our attendees understand what I3C is rapidly emerging as the preferred choice over older interface protocols like I2C and SPI, particularly in high-performance, low-power applications. You're set to gain valuable insights into the key features of I3C, including its speed, power efficiency, and scalability, as well as its backwards compatibility with I2C. Here on Xpert Insights, we'll include a detailed comparison between I3C and other popular interface protocols, giving attendees knowledge, the knowledge they need to make informed decisions when selecting the best protocols for their design. That's a lot, and I'm excited to start. But first, let me introduce to you our guest speaker. Our speaker today brings over 10 years of experience in IC design. A cum laude graduate in electronics and communications engineering from DLSU, Animo. He placed among the top 5 in the 2014 ECE licensure exams, a true standout in the field. Since starting his career with Sinex as a design engineer, he has advanced to being one of our most tenured engineers and is currently a staff design engineer, where he leads a design engineering team. Known for his strong communication and leadership skills, he excels in coordinating cross-functional teams, efficiently managing project timelines, and consistently delivering high-quality results to many, many stakeholders. So please let's give a warm welcome to Sinex's very own engineer Earl Lacida. Okay, so Earl, are you still there? Okay. No, like go ahead and we can start. Sorry, I was just getting confirmation. Yeah, go ahead and start.
Of the number of devices is only limited by the address space in the line. Also, the capacitance of the bus line. So each device in the I2C bus has its own address, and it is used for establishing the connection between the master and the slaves. So this image here is a typical I2C bus. So we have your primary master, you have your secondary masters, and then you can have multiple slaves. So here, the SD and SCL lines are pulled up using a resistor to keep it at a logic high. So yeah, and then data is sent into the lines by driving the lines low. So I2C data is sent frame by frame. There are frames, and each frame is acknowledged by the receiving device per byte. So here is an example of an I2C frame. This is an I2C frame. So the data starts with a start command, start byte. Sorry, a start signal, and then followed by a 7 bit or a 10-bit address. After which there is a read write bit indicating what direction the data would go, if it's for reading or writing, and then followed by an acknowledge bit. So this is where the target device or the master acknowledges the transaction, and then afterwards, data will be sent 8 bits at a time, followed by another acknowledge bit. So it could be multiple data. Multiple data can be sent afterwards. And then after this, there is a stop bit, or this could even be a restart bit. So now, what is I3C? So I3C is short for Improved Inter-Integrated Circuit. It is an improvement for I3C created by the MIPI Alliance. So it solves issues uh, of popular interface protocols, such as the number of pins. There could be multiple pins, and power data rate. So for I2C, in the I2C bus, it seems simple, right? With a simple implementation. But if we have multiple slaves, we will need multiple interrupt lines, which is outside of the SDA and SA lines. We will need also maybe restart pins to be controlled by the master as well, and also maybe sleep pins that is needed. So that becomes an overhead in the implementation of the bus. It will be added additional pins for those sleep and reset pins. So for I3C, uh, it solves this by using only by eliminating the need for those other pins. So I3C also uses the same two-wire interface and also back compatible with I2C, but it allows for very high speeds up to 33.3 Mbps. So this is an example of an I3C bus. We have a primary controller, and we can still have secondary controllers if needed. We have the I3C targets, and also back compatible with the I2C target. However, if you have an I2C target in the bus, you will still need the out of band pins, but only for the I2C targets. For the I3C targets, the out of band pins are eliminated. So let's compare how is I3C better compared to I2C. So first of all, the one great advantage of I3C is its higher bitrate, over 12 times better compared to I2C. So for the initial original I2C standard mode, it only goes up to 100 kilobits per second. But we have more recent implementation of the I2C bus going up to 1 Mbps and even up to 5 Mbps. But this high speed mode and ultra fast mode have large limitations. For example, for ultra fast mode, I2C, there is a need for this is only for write. This is only a write only bus. So there's only a simplex communication only one way. And for I2C high speed mode, it needs a active pull up for the for the clock instead of having the so it has a different electric specification compared to the original I2C. So technically, the I2C mode of operation only goes up to 1 Mbps, which is the fast mode plus. However, for I3C, even at SDR mode, um, we have a speed of 12.5 Mbps, and then for HDR mode, it is multiplied twice. So for HDR DDR, we have 25 Mbps, and for ternary signaling, we have at most 33.3 Mbps. So another advantage of I3C versus I2C is the use of dynamic address assignment. So for I2C before, manufacturers would lock in the device address during production. So, if, for example, if you buy a sensor from a manufacturer, there is a specific um, static address assigned to that device. So maybe they could have a jumper pin to change one bit of the address, but that's it. You are limited with the address choice. So, for example, if you have 100 devices that you need to connect in the bus, or 100 peripherals, there could be one or two or maybe five devices with the same address, which is problematic. So you will need to find another manufacturer with the same functionality but with a different address. So it could be very limiting. But for I3C, the addresses are determined after the bus establishment. So the controller actually assigns dynamic address depending on the type of slave devices, or sorry, so the type of target devices within the bus, depending on the um, characteristics of those sensors. The I3C controller actually assigns those addresses for each of the bus. So there will be no uh, two devices with the same address. So it eliminates that problem. However, static addresses are still supported for I2C legacy devices if the bus is impure. So the impure bus means there are I2C and I3C devices inside the bus. Another advantage of the I3C, and this is one big advantage, is the support for in-band interrupts. So this means that additional interrupt pins are not needed. So for example, for those I2C devices, we will still need the out of band line. But for I3C targets within the bus, there is no need for the interrupt bus. So the interrupt line. So the interrupts are actually processed inside the SDA line, the data line, when the bus is idle or during arbitration. And then hot joining is also supported. So a target device can join the bus even after bus establishment. So this is useful for devices with sleep capabilities. And then I3C also has a standardized set of common command codes. So these are CCCs, common command codes, that can configure target devices individually or at the same time. So there is a direct and broadcast common command codes used to configure the device. So for example, if we want to do a reset for multiple devices in the bus, even all of the devices in the bus, um, I3C has this common command code for resetting all those devices at the same time or even directly, one at a time. So the I3C controller um, can configure all the devices within the line um, on different aspects or different configurations, um, like when to interrupt or when to reset or when to change settings, etc. So yeah, this is a yeah. This also allows. This is also the common command codes is also the mechanism used for dynamic addressing, which we discussed earlier. Yeah, and also it has very low power compared to I2C. So for I2C, it uses the open drain implementation we discussed earlier. So it uses the resistor pull up, but with that configuration, the bus can be very slow. So the um, the bus consumes current when pulling down the line. However, for I3C, the SAL line is implemented in a push-pull configuration. So this is an active push-pull. So the slow pull-up is eliminated, um, making it a lot faster. The bus making the bus a lot faster, and also the SDA line. Uh, the SDA line still has the open drain configuration, but only during arbitration. During data transmission, the line changes to a push-pull configuration as well. So further eliminating the large current consumption. So this makes the SDA and SL line more power efficient. So I3C also operates at a higher speed. So the bus is active for only a small amount of time, even when sending a huge amount of data. So we actually have this graph is when is the power consumption when transmitting a 1 kilobyte block of data. So these modes, these four, these are I3C modes. So, and then this is I2C 1 megahertz mode, fast mode. So as you can see, we have a very large difference in power with the I3C power being very small. So if we transmit a higher number of bytes, so for example, if we transmit 1 megabyte of data, the power difference will be much larger in comparison. Right. So we discussed I3C compared to I2C, and as the name implies, I3C is an improved version of I2C. So it's a given. So how does I3C fare compared to the other um, serial protocols in existence? So for example, SPI, UART, and CAN. So for that, let's have a refresher. Let's have a refresher for the other protocols. So for SPI, so SPI means Serial Peripheral Interface. So it is an interface protocol developed by Motorola in the 80s. So, however, the SPI protocol is not maintained by Motorola or any entity. So the implementation can be different for different manufacturers or designers. So the SPI bus has four lines. The MOSI, MISO, S-Clock, CSSS. So this is the MOSI is the master out slave in. MISO is the master in slave out, and then we have the system clock and the chip select. So this is an example of an SPI bus. So um, for the SPI, there could be multiple slaves. Um, Usually, the multi-master is technically for SPI, multi-master is not really implemented. However, there are innovations or implementations for SPI that allows for multi-master implementation, which we will not discuss today. But there are existing multi-master implementations for SPI as well. So for SPI, the slave which it will be talking to or communicating with will be selected using the chip select or the slave select line. So for each slave added in the bus, there is an additional slave select line. So which this is one big disadvantage of the SPI. So however, SPI can be used for full duplex communications. So you can transmit and receive data at the same time. And also, however, SPI has no particular voltage or data rate or addressing scheme. So it is dependent on the manufacturer or designer. So the SPI data rate also, since it is not really regulated, it is theoretically limitless. So, but still, it will depend on the electrical configuration of the bus. So if you have a very high capacitance bus, for example, if you have a lot of devices in the bus, there is still a theoretical maximum to that speed. So some advantages and disadvantages of SPI. First, SPI has first advantage of SPI is that it transmits pure data because there is no need for any preamble or any addressing, any start or stop bits. There's just if the slave is selected, it will transmit um, pure data. So that, but however, because of that, there is also no error correction or sorry, error detection or error. So, and then so there's no addressing protocol. So implementing the communication algorithm is easier, and then it can be used for full duplex application communication, and also the data rate is can be very high, but is only limited by the capacitance of the wires and the driving strength of the pins. So some disadvantages of SPI, it is unregulated, so it could vary very differently from different manufacturers. Additional devices on the bus requires additional wires, so for the chip select, and also for the reset, maybe, or the interrupt. There are also multiple other wires that further limit the connectivity. And then it does not allow, it does not have any error correction, no error checking, no acknowledgement of the data received. So it could be the data could be there could be errors in the data which is undetected, and also uses a minimum of 4 pins for one-to-one communication. The next, let's discuss the UART interface. So UART stands for Universal Asynchronous Receive Transmit. So UART is very old. So it's one of the earliest serial communication protocols. Um, Most notably used in our monitors using the RS-232 interface. However, historically, it was designed from telegraphy. So actually, the 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 protocol for making the lines, the data lines, um, usually in the logic high, is rooted in telegraphy because we need to they maintain the wires in a high voltage so that they'll know if the line is cut, especially during the wars, World War One and Two. So just some history tidbit. um, so the interface only has two wires. So it has the transmit line and the receive line. So just like SPI, UR can be used for full duplex, but it can also be used for simplex, unidirectional, or half duplex. So half duplex is one transmit or receive one at a time. So, however, unlike other protocols, UART is a one-to-one interface. So it does not support any multi-master or multi-slave configurations. So this is an example of a UART bus. So it's very, very simple. Um, so as the name implies, UART is asynchronous. So it has no clock line, as you can see here. However, uh, for it to work, you will have to have the voltage level, the data rate, and the voltage level, data rate parity, data size, stop period configuration, the voltage levels. Yeah, I mentioned that. It should be the same for both the transmitter and receiver. So just like I2C, UART also uses a frame way of sending data or sending a packet. So it has a start bit, then the data, which is 9 bits, and then another parity bit for data checking, for error checking, and then the stop signal. This could be 2 bits or 1 bit depending on the configuration, or this could be multiple bits depending on the configuration. Yeah. So advantages of UART: it only uses two wires, same as I2C. It can be simplex, it can be simplex, can be full duplex or half duplex. So for simplex configuration, it will only use one wire, and then it has an asynchronous design, so no clock line, and so the synchronization is within the bus. I mean within the hosts, and then UART has been used for a long time, so there are tons of documentation, and also there is an error checking in the form of the parity bit. However, some disadvantages. It is only one-to-one communication, so it severely limits the application. So UART can be used for a long range, but because of that, it also limits the baud rate or the maximum data rate, which is limited to a maximum of 115.2K baud or 92 kbps, 92.2 kbps. And then another is that the configuration for the both devices within the bus needs to be established beforehand. So if you have two different devices, your devices with two different configurations, they cannot communicate with each other. Okay, and then the CAN interface. So CAN stands for Controller Area Network. So this is a multi-master broadcast communications system developed by Bosch. So CAN is much like I2C in its configuration, using also a two-wire network, and it has a built-in error detection and data error repair schemes. CAN is also regulated, so it is ISO. It is defined in the ISO. So ISO 11898. So it has uh, very well defined electrical um, and and algorithm uh, protocols. So it also has the capability to broadcast to all nodes. So this is an example of a CAN line. So unlike other communication protocols that uses ones and zeros or binary communication, the CAN bus uses a differential bus. So this means that it is not classified as high or low, but as a dominant or recessive. So for example, in this bus, we have the CAN H and the CAN L line. So when there is data or when there is no data, the line is hovering at a 2.5 volt state, for example. But during a dominant state, so when it's hovering at a 2.5 volt, there's no difference between the voltage between CAN H and CAN L. However, for a dominant state, there the CAN H is pulled up, or the CAN L is pulled low, or to a higher voltage. I mean, CAN H is pulled up to a higher voltage, while CAN L is pulled down to a lower voltage, making a differential signal along the bus. So for in this example, the CAN H line is pulled into 3.5 volts, while the CAN L line is driven into 1.5. So there will be a 2 volt differential signal along the bus. Yeah. So much like I2C, the CAN also uses a frame. So the first is the startup frame, and then there is an 11-bit identifier, which is the device address, can be which acts as the device address. And then we have the RTR, which is the remote transmission request. So this is like the read or write command bit, read or write bit. And then we have the IDE, or the single identifier extension. So the CAN frame can have two configurations. So one has an 11-bit identifier, another has an 11-bit identifier plus the other one has a second identifier. So for our discussion, we'll just discuss this first one. So RSV, this is a reserved bit, and then we have a 4-bit DLC. DLC means data length code. So this indicates how many data bytes will be sent next. So, and then there is the data. The data can be 0 to 8 bytes long, not more, not less. So only 0 to 8 bytes data. And then afterwards, there is a 16-bit CRC code. So this is a checksum for error detection. And then there is an acknowledge, and then the end of frame. And then after the end of frame, there is a period of idle, pass idle. So that's the IFS, or the interframe space. Yeah. So since the CAN interface is asynchronous, the devices in the bus need to wait a set period of time. So this is the IFS. So it has to be the bus needs to be inactive for a set amount of time for any one device in the CAN frame to begin transmitting data. So the startup frame is a dominant bit. So this startup frame, it is 1 bit dominant bit, which is used to synchronize the nodes in the bus after being idle. And then um, after the bus idle time, there could be more than one data that wants to transmit at the same time. So it uses uh, the same it utilizes an arbitration algorithm with with the device with the lowest identifier, the lowest ID, uh, will win in that arbitration, and the device with the lowest identifier will begin transmitting. So if the yeah if there are two or more devices, the one with the lower identifier will win the arbitration and start um, will continue transmitting. So this is the same concept used by I3C as well, the arbitration. So some advantages of CAN. So its use of differential signaling makes the bus very robust against noise because of the 2 volt difference within the line. Uh, so for example, if there is noise going, or there is a spike, a voltage spike going high, the CAN L signal will not be affected. So it eliminates it will not be detected by the devices. The noise will not be detected. So making it very fault tolerant. And then it has 16-bit CRC. It has the acknowledge, and also the data length code within the bus. So the data. So there is a very robust error detection for CAN. So it has the checksum, the acknowledge, and the DLC. Also, each device in the bus does bus monitoring. So it checks the data that it sends. And if the data it sent is not the same as what was reflected in the bus, it also monitors that error. So, yeah. So, overall, the CAN interface is very robust with its error detection. So the CAN protocol is also an ISO standard. So it is well documented. Only uses 2 wires and can be used for long range application, but with a low number of nodes. So it can be used for multiple amount of devices, but for shorter distances. So for example, if you have a longer CAN bus, you will be able to use only a smaller amount of devices. So because of the characteristic of the wire, of the line, it can be very high. The capacitance and resistance can be very high for a long line. So disadvantages of CAN. So there is a huge data overhead. So as you can see here, you can only send 8 bytes of data at a time. However, the frame consists of many other data, which is many other bits which are not data. Those are not data. So you have the 11-bit identifier. If you have the extended, you also have another set of identifier bits. So it could be very big, and then 16-bit CRC. So that's like 30 plus bits of not data plus with only 8 bytes of data. So the overhead could be very huge. And then because the CAN protocol can only send 8 bytes of data per transaction, so again, the overhead is very high. And then the CAN protocol is very um, particular with how you terminate the bus. So the bus needs to have proper termination because there could be signal reflections within the bus, so especially if the bus is very long. So you need to maintain the characteristic impedance of the line if you need to remove or add more devices in the nodes. So because of this, you cannot just remove any of the devices within the bus or add. You need to check for the impedance of the line. And then due to the built-in error checking and fault fixing capabilities, the protocol could be very complicated. So you have because of the so since we have to add the CRC, acknowledge DLC, and the checking of all those data, the protocol or the algorithm in implementing CAN can be very complex. So let's discuss the issues of these legacy protocols. So first of all, one glaring issue for the legacy I2C and SPI devices is the hardware complexity, especially with multiple devices. So each device needs a dedicated chip select and also dedicated interrupts and reset pins. So also there could be limited or even a lack of error detection for so for SPI. There is no error detection or handling. For I2C, there is only the acknowledge to ensure that the data is received. So for UART, you only have the parity. However, for CAN, it has a very robust error detection. And then you could have a lack of documentation or standardization. So for SPI, it is unregulated. I2C is also unregulated. However, for I2C, there exists some implementation specifications, so especially from NXP. However, it is still unregulated, so there is no regulating body for I2C. So also there could be slow data rates. So for UART, as we discussed earlier, the data rate could only be 115.2 kbaud. For CAN, it is limited by the distance. For CAN, the maximum data rate is 1 Mbps, and so, even slower for long distances. So how does I3C solves these problems? So first, for the hardware complexity, I3C strictly adheres to a two-line bus, especially for a pure bus. If the bus only has I3C devices, you can be sure that bus will only have two lines. So, however, if you have I2C slave devices that you need to add in the bus, it will still have the cumbersome interrupt pins, the interrupt, reset, and sleep pins. So, so for I3C, the IBI or the in-band interrupt eliminates the need for additional lines. Also, the use of the common command codes eliminates the other pins such as reset or sleep because the configurations can be sent directly within the line, within the SDA line for all the devices inside the bus. And then also new devices can join the bus even after bus establishment using the hot join feature. So yeah, you could be free to implement the bus even with limited power or limited pins. So for the lack of error detection, I3C uses multiple error detection features such as the ACK or NAP. It still has the acknowledge, and now it has the parity per byte compared to I2C. And then also uses a 5-bit CRC during HDR/DDR transaction. It also uses the same concept from CAN, which is the bus monitoring, wherein the devices within the I3C bus checks what data they sent or in the data line to check if there is any discrepancy. So there are multiple error detection and handling protocols inside the I3C protocol. So it can detect for example, it can detect if the bus is stuck, the SDA data line is stuck, or etc. So SDA monitoring, etc. And then the issue with the lack of documentation and standardization for I3C, it is maintained and regulated by the MIPI Alliance. So yeah, the I3C protocol specifications, implementations, verification, even the electrical specifications, and testing. These are all maintained and documented by MIPI.
Recording stopped.
Sorry. All right. And then for the I3C, also it solves the slow data rate by it also solves the slow data rate problem. So uh, I3C operates at an SDR rate of 12.5 Mbps. At HDR DDR, twice that, so 25 Mbps. And at ternary signaling modes, it has a data rates up to 33.3 Mbps. There. So I have this comparison table, which you can snip. Uh, so uh, if you will learn anything from um, this seminar, I think uh, you would want this table. So this is a clean comparison table of the I3C compared to the um, other interfaces that we have discussed today. So as you can see, I3C has synchronous clocking. Most of the others are also synchronous, and sorry, the UART and CAN are asynchronous, but I3C is still synchronous. So one advantage of synchronous clocking is that you do not have synchronization issues. So the data rate very high compared to everyone except for SPI. So as we discussed earlier, the SPI data rate could be very high, but it is only limited by the capacitance of the bus and the driving capability of the ICs. And then uh, most are short distances, can be used for short distances, except for the UART and CAN. So, and then for bus configuration, I3C utilizes open drain and push pull. The others use differential or pull up, push pull, or open drain. And then I3C has robust error detection comparable to CAN. However, the protocol complexity can be high also for I3C comparable also to CAN because of the error detection and handling. And then maximum devices in the bus limited only by the address space. For CAN, it is limited by the transceiver strength. The others limited by by the physical implementation. Multiple master supported, and then number of wires, 2 wires only. Yeah, and the protocol is haptoplex. So yeah, so what applications can we use I3C on? So uh, one one application is for mobile and wearables. So as we discussed earlier, the I2C bus has a manageable, so it has only 2 wires, and very low power compared to other protocols. So it can be used for mobile wearables that uses batteries and also has very limited physical space. So again, using the same advantages, it can be used for IoT or Internet of Things. So, and also being back compatible with I2C devices. If you have uh, an existing bus or an existing network, you can upgrade to I3C easily without even if you have I2C devices within that bus, because those I2C devices can be are also supported for I3C, and then also can be used for automotive or automotive applications because of the robust error detection and handling. Also, with the higher data rates, you can have real-time sensor data for automotive applications, and also for industrial applications. So, because of the increased data rate of the bus and also implementing of the in-band interrupts, you can have more sensors implemented within the I3C bus. So, for example, for industrial testing equipment that needs a lot of sensors, you can have just one bus to cater all of those sensors. So, for a conclusion, I3C is a modern interface protocol. So, it solves all those various problems of the existing legacy protocols that we have. Um, so, it has a high speed bitrate, low power, and robust error detection, all while maintaining the same simple two-wire physical interface. So, um, its modern design makes I3C the interface protocol of choice for any future-proof communication bus design in our high-speed, low-power chip industry. So yeah, that's it for my presentation. Thank you everyone for listening. I think any industry with the, for example, that needs high speed. So, for example, imaging or uh, that needs that needs like real time data gathering. So, for example, for uh, mobile, for small devices like watches, for example. If you need, yeah, if you need, yeah. Yes. So, yeah, it can be used for all the things that I2C was used before. So, but with higher speeds and then with more robust error detection and also very flexible in terms of implementing devices from multiple manufacturers. So it can support because of the advancement with the dynamic addressing, etc. It can be integrating sensors from multiple manufacturers and designers are easier than ever before. So yeah, for security, well, the I3C bus doesn't really for the security it is actually depends it actually depends on the implementation of the designers of the network. But I3C can be used for uh, for high speed communication between those devices. So, for example, you can have flexible signaling. For example, if you want to reset a device that you deem may be compromised, so you can use I3C bus to easily communicate between those devices and then send configurations or commands to those devices if you have if you think they are compromised. So that's one. Yeah. USB and PCIe. So the USB and PCIe are different monsters. I mean, different different. I mean, they're different interfaces compared to I3C. So, for example, PCIe uses parallel communicate. I mean, it is a parallel bus. That's why it's very fast. And USB is usually used for PC. I mean, for physical devices. For I3C, it is used for more discrete devices, more smaller implementations, for example, chip to chip communications instead of device to device. So it can be used for more discrete systems that needs less. I mean, there are systems that needs less speeds compared to USB because USB-C goes up to 40 gigabits, I think, now. Yeah. So for more limited or even for smaller designs, smaller systems, I2C could be your go-to. Yeah. Yeah. And thank you for those questions. Yeah, very good questions. I mean, thank you for those questions. They are very good questions to ask. Yeah. Yeah. So for all the designers or all the participants today who's thinking of designing their uh, their own systems, maybe check out I3C. It is yeah, it is a modern interface for faster communication. So if you have innovations involving maybe imaging or sound or even AI for communicating between different chips, you can always use I3C to make it faster, more reliable. Yeah, that's all. And I hope you guys learned something today.
And thank you everybody for attending. I really do appreciate all the ones that greeted us good morning. Apologies that we haven't actually greeted you back, but thank you. It's acknowledged. Even those on Facebook, we appreciate. Um, so before we officially sign off, again, a few reminders. Um, if you do want to obtain the certificate, please go onto the link and sign on. I'm sure there's the link is coming on screen now. We have until 12 p.m. For you guys to sign on. If you don't, you won't be able to get the certificate. And this isn't by no means our last webinar.